Hello, welcome to the fourth installment of our discussion on orthogonal circles, um, or rather, equal circles and orthogonal points. So, if you have looked into the previous three videos, you know that we want to show that angle O1A02 is equal to angle BO3C. Now, there are several ways of looking into this. The first thing that you have to realize is that we have a number of rhombuses in this picture. So one of them is, let me mark it with a different color. Maybe I'll mark it with red. One of them is this. This one is a rhombus. And the reason it's pretty simple, if you look into the opposite sides or all sides of this quadrilateral, they're all radii of equal circles. So this is a rhombus, which means that the diagonal, this line, the diagonal, divides this angle into equal parts. And the same thing goes with this quadrilateral. That's also a rhombus. And these two angles would be equal. So in another way to say this is, if you look into this angle, suppose this is x, then this one is x. And if this is y, then this one is y. So this full angle here is twice the angle that's here. So the full angle is this much, which is 2 times x plus y, which is basically angle BO3C, which is one of the angles, right? And the angle here, which is x plus y, that's angle O1, O3, O2. That's x plus y. That's exactly half of this angle. Now, there is something very interesting going on in this picture. If you look into the triangle O1, O2, O3, let's mark it. The triangle O1, O2, O3, that clearly has H as the circumcenter. Why? Because HO2, HO1, and HO3, all of them are equal, right? HO2, HO1, and HO3, all of them are equal. They're radii of equal circles. So H is a point which is equidistant from O1, O2, and O3, which by definition means that it's the circumcenter of the circle passing through O1, O2, and O3. Is the circumcenter of the circle passing through O1, O2, and O3. Now this is a big deal. Why? Because then O1, O3, O2, this angle becomes an angle in the circumference, and this angle becomes angle at the center. So angle O1 HO2 becomes the angle at center. That would be twice angle BO3C. That would be twice of angle at the circumference BO3. O1 O3 O2. This is O1 O3 O2. And we know that angle O1 O3 O2 is half of BO3C. So twice of O1 O3 O2 is nothing but angle BO3C. So this is a simple angle chasing, but with the observation that H is the circumcenter of the circle passing through O1, O2 and O3. And BO3C is exactly double of O1, O3, O2. So a little bit of angle chasing, a little bit of circle geometry going on here. So what do we get? We get this angle is equal to this angle. Maybe I can mark it in red. So this entire red angle is equal to this entire red angle. And notice that AO1HO2 is again a rhombus for the same reason, is a rhombus. So opposite angles of a rhombus are of course equal. So we get this O1HO2, this angle is equal to this one. And that's precisely what we set out to prove, right? We wanted to prove that O1AO2, that is this angle here, is equal to this angle BO3C. That's what we wanted to prove. If we have shown, now that we have shown that, we can say that AO1O2, this triangle, is congruent to BO3C. So let me write that. Triangle AO1O2 is congruent to triangle BO3C because obviously these sides are equal. They're all radii of equal circles. And now we have shown that the included angles are also equal, which would mean O1, O2 is equal to BC. O1, O2 is equal to BC. So O1, O2 is equal to BC. BO1 is equal to CO2 because they are radii of equal circles. So now we have this as a parallelogram. This is a parallelogram, which is what we set out to prove in the first place. So I hope you understand this particular solution, and if you don't, of course, ask questions in the support forum. There is a link in the description for the discussion page, and you will also find the support forum there. Thanks for watching, and you can subscribe for new videos on Olympiad and other advanced mathematical topics. See you in the next video.